I think we can have Hao's presentation now. Hao, the floor is yours.
So I have shared my screen. You can see it, right?
Yeah, we do see it here. And
good. Thank you. I hope you have had a nice day yesterday and this morning. Good to be the second. And thanks, Maarten. You have set the scene, so I don't need to repeat some of the stuff. But I agree. I mean, Maarten has brought some really good topics on the table. I just want to supplement and add some more taste into this topic. So technology, TEG, I don't need to explain what the company is about. We're doing thermoelectric generators. We're spin out from university about 13 years ago. So when I'm asked what's our biggest difference between technology and other thermoelectric companies, I used to say we're still in business after 14 years. It's not easy because commercialization of thermoelectric is not easy. It's so damn hard. Well, the background, I still want to bring it up, is how do we power our future with increased energy demand while reduce the carbon emission? And also, when we try to generate more sustainable energy, how about the efficiency of the existing systems? And now more and more people start to understand that the greenest energy is the energy that we don't use. That means if we can save the energy, maybe it's more important than generating new energy. The third one is, as we talk about big data, AI, which is absolutely the hottest topic nowadays. In the industry scenario, we're talking about powering millions of sensors, and then you're using a lot of batteries. And how can we avoid using the batteries? And here we propose that thermoelectric can play an important role. So again, I don't need to explain how thermoelectric works, but here you can see TEGMAT, which is the brand of technology. We managed to make a flexible TEG. So basically, when you look at it, the principle is very simple. So, but we put the bulk. We're still using bulk materials and P and N type materials and build them into a flexible substrate. I mean, the solution is patented. So it's not because we want to hold it tight. I mean, just because we want to stop our competitors from stopping us to do so. So I'll be very, very happy to disclose all the details because we believe that there's some unique advantages of having a flexible TEG. First of all, it's much easier and more robust to apply it on non-flat surfaces. So the adhesion to the heat source becomes much easier. And also the thickness of our substrates are much thinner than ceramics. Also makes heat exchange rate a bit higher. And this design is not specific to any material because it's flexible. It doesn't require a high match of the thermal expansion. That means we can, in principle, build different materials into a single module so they can expand their own pace. So the substrate can absorb this expansion. And also, as the start, but also some other projects that we're working with, we're trying to replace bismuth telluride. If we talk about large-scale applications, bismuth telluride material cannot meet the needs. There's not enough tellurium on Earth to support thermoelectrics. So we have to use find alternatives. And in technology, we're using zinc antimonide and the magnesium antimonide as our materials, which both are very abundant and very affordable. With that said, this is a little bit technical, so this is just to show that our flex module is at least as good as the market state-of-the-art ceramic-based bismuth telluride modules, plus we're flexible. To the right, you see the ceramics, of course, it will crack as soon as you bend it at 0.62 degrees. And for ours, after bending at 20 degrees, after 250 cycles, there's no breakage or degradation at all. But okay, when we have this, does it mean that it's easy to commercialize? And the answer for me is absolutely not. For people who know me for a while, you know, I'm cautious, cautiously pessimistic about the future of thermoelectrics, because for me, we are falling behind compared to other technologies. It is a very uncomfortable truth for me, even though I've been staying with thermoelectrics for all my career, I've been staying with the company for all these years. I want to see commercialization, a success of thermoelectrics. But the fact is, there's a lot of dilemmas in front of us. The first one being the technical development and the market pull. As we know, we can do a lot of things in labs. And also we can also do a lot of prototypes that we think we can generate some power. And we're excited about these solutions. But the thing is, there's other saying, so they say prototypes never fail, but never scale. And on the other side, as Maarten said, when you go to the market, when you try to sell this solution to customers, either end users or someone who pays for this to build this into their system, they are looking at something completely different. We all know this, the correlation between the ZT value of the material and the efficiency. And people also always claim that when we have the ZT, a material with ZT of 4, then we're disrupting a lot of industries, including cooling, compressor, even racking cycles. But the thing is, it's not harmful to imagine, what if we will never find a material with a ZT of 4? And what would that happen? Does that mean that there's no application for thermoelectrics at all? Apparently, the answer is no. So the idea is we need to find applications where our existing material, our existing solutions can meet the needs. So technical development and commercialization should go hand in hand, not one after the other. We should not wait when we have a perfect material, when we have a perfect module, then we start to look at where to put this into the market. No, we should look at already now. And also here, it's a general trend of the ZT development in the last 80 years, 70, 80 years. So we see a significant increase of the ZT. Of course, some of the results are still to be approved, but let's assume they're there. So the ZT has increased. But then what will happen here? I try to compare TEG thermoelectrics with solar cells. So sorry about this busy slides, but the thing is, if we look at the trend, in the 80s, where solar cells just about to be on the market. And if you still remember, at that time, the only application is the small window on this pocket calculator. And that's the biggest market for solar panels. And after 30 years, now everyone wants to build a solar cell on their roof. So if you look at this blue line, which is the silicon-based either single crystal or polycrystal, which is the mainstream of the solar panel, it starts with the efficiency of 12%, which is not high. Now it reaches 20–25%. If we look at this, the efficiency of thermoelectrics, starting from 90s, now we are about to reach 10%. In good case, maybe 12%. So we are at the stage of when solar panels start to be really explosive. But does it mean that we can expect a same explosion of implementation of thermoelectrics? I don't have the answer, but my feeling is probably not. Because we cannot compete with other technologies already on the market. And people like to compare TEG with PV, with solar panels, and so do us. As I see it, solar panel is not the best way of using the energy from the sun. Right? As we all know, if you look at the spectrum of the energy of the sun, there's only tiny bit, which is visible light, that is utilized by solar panels. The vast majority of the energy provided by the sun is actually thermal energy, it's the heat. It's supposed to be used by thermoelectrics, right? If we do it, push it to the extreme. But the thing is, thermoelectrics has already passed this commercialization window of utilizing the sun, because all the places are already be taken by solar panels. And there's no way that thermoelectric can still compete with PV, even though we have, assuming we have high efficiency than PVs. When PV starts, we already missed the window. We cannot compete. We cannot take the place that have been taken by solar panels back. So then the question is, we should find the applications where thermoelectric is unique, and we don't compete with a technology that will never have a chance to compete. This comes to this diagram. So if you look at the cost and the value, so everyone likes something cheap and brings a lot of value, right? This is just the market, very simple. We don't want to go there. We don't want to buy something which is very expensive and have less value. And then for thermoelectrics, so far, the best application so far is the RTG, the radioactive thermal generator, which is used by NASA for the deep space probe where even sun cannot provide enough energy. They use radioactive material to generate heat and then convert heat into electricity, which is a super reliable and robust solution. So the first, the two probes that have been built into Voyagers are still generating power after 50 years. That prove the reliability of thermoelectrics. However, that application is completely different from what we're talking about today. In that application, people care less about the cost. They care something else, the reliability and so on and so forth. And that's also why the existing thermoelectric modules look like this. If we ever think about why does thermoelectrics have to be built into two thick ceramics, that's because it was designed for deep space applications. It was not designed for industrial application. And then for me, I will put thermoelectric cooling into this corner, which is low cost and low value. And then all the existing thermoelectric generator applications, I call it niche applications. These camping ovens, maybe also military. They are very small markets. And the question is, what's over here? Can we find an application where it's unique for thermoelectrics, that we can bring affordable material and generate lot of value? I don't have the answer. And here is also, as mentioned, technology, even though the thermoelectrics, even though as a promising emerging technology, we are competing with many potential solutions. And even if you say in some unique applications where we have no competitors, but then we're still competing with status quo. That means we're competing with people to motivate people to change from existing solution to thermoelectrics. So remember, we're always competing with status quo. That's actually the biggest challenge for thermoelectrics now. If we put, well, here we put a technology as a company, we can also put TEG as the entire solution in the middle. So instead of competing with existing technologies, maybe we can think about how we supplement or how we interact with existing solutions and industrial sectors. That gives us another angle of looking at not doing this either or choice, but we're doing both and. So how do thermoelectrics add value to the existing solutions? Here is a flow chart that we make. It might look different for different thermoelectric manufacturers, but they more or less looks the same. We start with the raw powder, raw materials, right? And then we mix the powder, and then we bake it, we synthesize it, and then we grind it into fine powder again before we do either hot press or SPS or heap or whatever method that we compact it into dense pellets, because we need dense bulk material to be built into modules. But before doing that, we also need to put buffer layer, put barrier layer, and put electrodes on those legs, because they are semiconductors. Semiconductors need these different interfaces to be connected by metals. And then when we have these pin and nail legs, we can do pick and place, and then we can build them into either we use tin soldering or silver soldering or welding or whatever method to put them together into the sandwich structure. What the question is, this is the supply, this is the production procedure. Has this procedure aligned with the application? Also, as Maarten have said, it's not sufficient to come with a product. We also need to motivate the entire supply chain. We need to have people who are motivated to supply their solution for thermoelectrics. Or they need to see business, let's say, for using their, let's say, pick and place machine. Instead of assembling smartphones, now we're asking them to assemble thermoelectric modules. Those people need to see value in doing it. And we are the people who should tell them and show them that there's real business into it. I think this is the biggest challenge for the entire thermoelectric society, that we don't have a reliable supply chain. We're counting on some other industrial procedures. We borrow their procedures to produce thermoelectric materials. And that makes things very expensive, difficult to scale, and difficult to promote. So we really need to rethink the holistic solution of the supply chain and value chain. How do we put things together? And here for TEGnology as a company, we see this as a huge task. And in order to solve it, we need to have some low-hanging fruits or small wins. And this is the market, Industrial 4.0 or digitalization, is the market we think might be some low-hanging fruits. Because, as I said, people want to install sensors everywhere. people want to collect the data from all difficult places. It's not just about the cost of batteries, which is very affordable. So let's stop saying that thermoelectric generator is competing with batteries or replacing batteries. People don't care. And honestly, I don't think thermoelectric module can ever compete with batteries, because batteries is an established company, huge company, and still improving. And the batteries become better and better, cheaper and cheaper. So if we're saying technology, a TEG module that costs, I don't know, 20 euro, or even 10 euro, or even 2 euros, is still very difficult to compete with batteries. So we really need to bring more value to the solution. That means the accessibility to power. When you use batteries, you need to know where the sensors are. You need to put them into accessible places, because people need to go there and change it. And also in some difficult, critical places where battery doesn't work, for example, high temperature, high moisture, high vibration, and those places, TEG is unique. A real case is district heating, the underground pipelines. While we are enjoying the hot room or nice warm room or the cold room in the summer, someone has to go down to these manholes to monitor the underground pipelines. And monitoring of these pipelines is difficult. They are using batteries. And also when something went wrong, the pipe starts to leak, it takes a lot of time to find. Not to mention now they're talking about digitalization of district heating, so they are collecting real-time data so they can adjust the energy distribution in real time. All that relies on many data, which battery cannot support. So the solution is we put a power supply unit with TEG onto the hot pipes with a few degrees temperature difference between the hot water pipe and the earth. We power sensors and send the signal directly from underground. And then suddenly we build a digital twin. So apparently the value there is more than the amount of power, the amount of electricity, some several milliwatt. It's far more than that. This is another case where we integrate a TEG into a piece of concrete, a cement block, and then build this into a building. And when the indoor and outdoor temperature difference exceeds 6 degrees, and then this piece of concrete starts to send wireless data about the temperature and the moisture. So we turn a piece of concrete into an element of the smart house. There also, people don't calculate how much power we're generating. They count on the uniqueness of collecting data. Then another use case is industrial low-grade waste heat, as Maarten has already mentioned in the first talk. We are wasting a lot of energy, the energy that we get by burning fossil fuels. When the temperature is below 200, even 150, it's getting tricky to reuse them. People will say they would rather just throw them out of the chimney instead of reusing them. And then we say, okay, what if we can produce large-scale thermoelectric generators with a very affordable price? So we can cover, let's say, 1,000 square meters, covered it with TEGs, and then let it generate power days and nights. And then actually, it's not how much power we can generate, it's how low. So the question is how low we can produce those TEGs, because we need to implement it in very large scale. This is also related to how we're going to produce them. It's entire value chain that we need to restructure, entire supply chain. A third possible application is wearables. We're using human body as the heat source. The concept has been there for decades, and many people in the industry, in academia have been trying to do this. It can be done. But again, when it comes to wearable devices, medical devices, it's not that easy. It's very tricky to get approved, so it's a long shot. But it's absolutely a potential. And here's how we see the scalability of thermoelectrics. We start with industrial sensor, power industrial sensors, and then go to the large scale, low grade waste heat into the future wearables. So this is how, this is the slides I personally like most. It's how we create value for thermoelectrics. It's not only the technical values that we can convert heat into electricity. It's for energy, let's say for energy sector, we can actually increase the energy efficiency. So we increase the profit of end users. And also if you go to environmental, we reduce the greenhouse and we use less critical material like tellurium. And also for this, on the societal level, we optimize energy efficiency. And the same goes to IoT and wearables. So this is what I want to talk. As you can see, there's a lot of things still to be done in front of us. But this is not too late. I mean, it's not only too late, and we have to think application to take the supply chain and end users hand in hand while we're developing new materials, new modules, because we need input to make our TEGs more relevant. And then I'll be happy to discuss if you have any questions or comments.
Well, yeah, like before, we have just a few minutes left before your half an hour is finished. So maybe if there is one question already, we can take it, and then we move to the next speaker, and then we will have the final Q&A. Is there any question? And also from the people connecting remotely, of course, if you want, you can raise your hand and your microphone and ask. Is there any question from the room?
Well, if not, yeah. I have a small announcement, a very small announcement.
Yeah.
So,
yes,
on the 26th of September this year, TEGnology is organizing an industrial workshop on thermoelectrics. So this will be focused on industrial audience. So we will not talk about, band structure or new materials or ZT. We will talk about the existing applications. We also invite people from industry with less knowledge in thermoelectrics to let them speak how they think thermoelectrics. If they are going to implement thermal energy harvesting, what needs to be there? So we're really turning the table around to say, let people tell us how they want thermoelectrics to be. I'm just showing a preliminary speaker here. We will invite politicians from EU level. We're promoting thermoelectrics as the energy material. And also we will have people from Japan, from Korea, which are typically the front runners in commercialization to have a global view of the application. We also have local partners like Danfoss and some industrial IoT companies, which are already adopting thermoelectrics to see what are the bottlenecks, what challenges are they facing, on top of the technical challenges that we are facing as TEG workers. So I will share the link somewhere in the chat, or maybe in later on I can share. So you're very welcome to join. Yeah, that's it. 26th of September in Copenhagen.
Yeah, I think there's a question from, maybe we take it now, we still can take it now, maybe. There's a question from the audience remotely. I don't want if you want to speak, from Rishikesh Kumar, or maybe I read it if you don't want to speak. He says, you're talking about cost. So how to reduce the cost of TEG meanwhile enhancing the efficiency?
Well, good question. Good question. So again, we don't want to look exclusively in the material on the module, because we can easily end up in a very poor solution when we start with the best material. So it's not only the material, it's really the material needs to be built into a component, a TEG component. The TEG needs to be built into a working system where maybe we need to think about the interface and how we create a bigger delta T. Do we need active cooling, passive cooling? And also, what is the grade of the heat? Is the high temperature, mid temperature, low temperature, and all that? How do we utilize the electricity? Do we convert it and send it back to the grid, or we put it in the battery, or we use it immediately? And all that will influence the overall cost of the solution. It's not only the cost of the material, because if you look at the entire value chain, the material cost is just a portion of it.
Okay, thanks, Hao. I think we stop here now for your part, and we move to the next speaker, but stay connected because we will have the final Q&A. Yes, so we come to the third speaker for today. It's Jean-Yves Escabasse, who is also a scientific advisory board member for our project. But he is from CEA, and he will talk about a new project, Horizon Europe project called STARTREC, which looks fancy. So I hope everything is set. I think we just have to move the camera, but it's almost ready to start. Move the camera.
I don't think it will be possible to record.
Okay, good morning everyone, and thanks to the START project for giving me the opportunity of introducing our thermoelectric activities at CEA and this brand new project. So I have to warn you that this project is being negotiated with the European Commission. It's been accepted for funding in the last call of spring, and we are still negotiating some minor points. So that's the only reserve I want to make on this project. But I think we are all thrilled to start working on very challenging matters. So I will explain you maybe on the long way how we came to propose additive manufacturing for thermoelectrics, and then I will give a general presentation of my lab, remind you of what additive manufacturing is. This is a group with expertise on thermoelectrics, so maybe you're not very familiar with AM. I will explain the benefits of AM in TE, and then I will illustrate these statements with a few comments on STARTREC. So we belong to CEA. This is the French energy, atomic energy and alternative energies commission. We have a complex mission statement, low carbon energy, digital future, healthcare, and defense and security. So I'm working with the low carbon energy division, and more specifically at LITEN, which is one of the several institutes in this division. And LITEN is equipped with, you have a problem?
Just a small.
Oh yes.
Yeah.
Oh yes, it's also online, of course. Yeah. Thank you. Thank you. So these are our 12 technology platforms. So very diverse, but all oriented to low carbon energies, and with excluding nuclear. Nuclear is not involved at L10 at all. So you can see fuel cells, solar, carbon conversion, hydrogen production, etc. And we will be busy only with the powder metallurgy and plastics processing and assembly platform. So the Poudrinov platform deals with materials for energy, with some works on processes, on materials and architectures to reduce energy consumption, to reduce material demand, and to increase performance. Yeah? And we do that on a lot of different materials, be it metals, polymers, ceramics, for very broad industrial fields. So we started this platform in 2012 already, so it's 2,000 square meter facilities. We have 65 people, altogether 12 million euros investment. So this is for plastics processing and powder metallurgy. We started with powder injection molding and extended progressively to permanent magnets, metal and plastics and ceramics AM, and more recently solid oxide cell workshop. So this is for high temperature water electrolysis production. So now focusing on additive manufacturing, also known as 3D printing. So the aim is to produce 3D objects layer by layer, and this is all steered by a computer. The machine is commanded by a computer. You have a couple of pictures showing you the benefit of using this technology. The more complex the part is, the better it is to use AM. Otherwise, we're not competitive versus more conventional technologies like milling or casting, of course. It has to be complex, and there are many applications. The applications you see on the left part of the screen have different maturity levels. So regarding medical implants, dental is really already in the market. Aerospace industry, it's coming. Automotive industry, we have a hard part here, given the volumes and the cost requirements. So it's really hard for AM to penetrate these markets, but these are all fields of interest. So there are a huge lot of technologies available on the market. There are still others that are not illustrated on this graph, but we are going to talk already today only of SLM, selective laser melting, but this is a trademark where we speak of powder bed fusion laser. So this is the only technology that we are going to talk about today. The principle is that to draw your parts with a CAD, with a computer, then send this to the machine where the powder bed will be laid layer by layer. The powder is spread, then the part is written by a laser, then the next layer of powder is laid, and so on. Yeah? And so little by little you're building your parts. Just finishing the animation. So this is how you get your part. So after, when it's finished, you have to shake out the unmelted powder, get your part, clean it, polish it, and finish it. So everything happens in a very, very small area in the machine where the laser beam meets the metal particles, melt them. You have a large number of physical phenomena involving very high temperature gradients, and this has influences on how the material the part is consolidated, creating tensions and so on. So that's a huge field for research and development, still under development. So AM for thermoelectrics is still a rising and emerging field. Basically, at CEA, we started this development 3 years ago. We studied two different materials, silicon germanium and bismuth telluride. Even in the state of the art, it's quite recent. The very first papers appeared in 2015. We found no reference at all on silicon germanium and the bismuth telluride. There are only 2 teams. Regarding silicon germanium, these applications we are targeting have already been described by my predecessors in this workshop, by Maarten and Hao. Why? Because we're talking of energy harvesting here. So if you really want yield and production of energy, you need to target high temperature. And silicon germanium is well suited for that. So it's now a 2.5-year development. With us, we have a PhD student. We have 2 important projects. The FAST project is already running. That's ANR, for those who know it. And we have just won this new project, STARTREC, which I'm going to show you afterwards. And after trying bismuth telluride within an internship, we decided to give up and concentrate on silicon germanium. The picture here shows you a possible layout of a thermoelectric generator as 3D printed. This is, of course, a mock-up made out of steel, but this is something that is thinkable with silicon germanium. So we have already published a patent, and we have 5 more in progress, and we also have a published paper which you can find from the internet. So why? So first of all, CEA has a long expertise on thermoelectrics. We've been working 20 years on silicides mainly. There are vapors and patents and so on. We've been working with enough platform, as I explained, for 7 years on AM technology. So the aim is, the idea is to combine both technologies. We started 2.5 years ago, and you see a picture of this machine. The Pro X200 is an old machine, but it's robust. We know it quite well. It's flexible. So this is where we are working. We have investigated silicon germanium and bismuth telluride, as I explained, and we have other materials in mind. It's possible, but this is a long shot. So this Pro X machine works with infrared laser, 70 micrometer spot diameter. And we work currently on a stainless steel plate, but more developments are possible. So why silicon germanium? So it's green material, non-toxic, relatively abundant. So both silicon and germanium are on the list of critical materials. But the volume of materials is not that big, and there are ways to make it green. it's a good thermoelectric deal for high temperature ranges. As I explained, the aim is to harvest energy, so we need to tackle those high temperatures. And you see these applications, they have already been mentioned by my predecessors. I'm going to mention them again with the STARTREC project. One advantage is that both N and P materials can be produced of the same raw material with different doping. And the advantage is that you get the same expansion coefficient. So that's really an advantage with silicon germanium. And it's quite well known, thermoelectric material, meaning that with our 3D printing trials, we can always compare and benchmark with other publications, other works. So this is on the left our first building plate, so it does print. That's the good news. We do get good density, close to theoretical, so that's the good news. Of course, there are some bad news. So you see here some pictures. So the top view from above in the building plate. So cut in the building direction. So it is a typical columnar growth for AM. This is very common here. You see that we get some cracks here. So as I said, 3D printing, metal 3D printing involves very, very high thermal gradients and with very strong tensions, mechanical tensions in material, and this is causing the cracks. So that's really an issue. And if we look at the EDS map, you see that there is material segregation. Silicon and germanium tend to separate, and even the dopant, phosphorus here, and material, is clustering. So this is not favorable to thermoelectric materials, of course, and this means that some annealing is needed, and this is a work in progress. And of course, the result of this is poor thermoelectric properties. So those black, red, and blue dots here are taken from the literature, and are our results, whereas the state-of-the-art, those green triangles are from the literature. So with ZT, we are one order of magnitude lower, and that's due to the poor electric conduction, mainly caused by those cracks, which we have to address. So the challenge is to improve this. First, to reduce the material segregation, so by activation annealing, and to reduce the thermal-induced cracking. So there are two ways of doing that. To use a heating plate in a 3D printing machine, this is a common solution, and to use nucleating agents. And this is also something that you find in state-of-the-art. It works for aluminum, for instance. Yeah. So this is work in progress, and this is why we have this PhD student. And this is being addressed in our FAST project. Now coming to STARTREC. So you all know that the state-of-the-art thermoelectric generators have a poor efficiency. This is due to rather low ZTs. So Hao has been mentioning this issue this morning. We have to cope with rather low ZTs, below 1. That's a fact. Thermal transfers are usually poor on TE devices, and TE materials are not well suited to real situations and hot and cold temperatures. And a lot of application use scarce and toxic materials. But thermoelectric generators are reliable and proven static conversion systems. RTGs have been mentioned several times, and they do work. They are noiseless, no vibrations, no moving parts, no maintenance is needed. And as I said, the reliability has been proven. So it's possible to work on that. So in our project, we will work on innovative technological bricks to make it work. We will work on innovative nanostructured silicon germanium materials using innovative technologies like AM, nano rapid casting, and Maarten, I always forget what the O means, but that's another consolidating technology. We will also work on optimized construction with complex shapes for both materials and devices. We will develop cascade architectures. I will show you in a while what this means. And of course, we will work on life cycle studies and reduction of critical material content, like always needed in European projects. And we will demonstrate this in 3 high-impact use cases. So again, always the same: waste heat recovery in metal industry, micro CHP in domestic pellet boilers, and RTG. Expected outcomes: increased performance, modularity, integration, eco-friendly approach, lower cost, and of course scientific breakthrough. This is a research and innovation action. So first technology brick, innovative TE materials and TEG architectures. You see here conventional microstructure A, and if you have a smaller microstructure, then phonons will disperse more easily, and you get lower thermal conduction. And you can see that on the graph, where using the HIP, that's high pressure. Bruno, remind me what HIP means.
Hot is the static pressure.
Hot is the static pressure. So this is a means for obtaining this small microstructure, and you see how the ZT increases by just reducing the particle size, the grain size in the material. So that's one thing that we are going to investigate in STARTREC. And the cascading architecture. If you use a segmented generator, the conventional structure, or the cascade generators, so one on top of the other, then you see that the power factor increases so much and the conversion efficiency increases so much just by superposing. So the cold side of the first TEG is the hot side of the next one. So this is something that we are investigating. Then the brand new additive manufacturing. So you see again a new design of a TEG, and on the bottom of the picture you see the results of some simulation. So this is simulation, it's not real, but the real thing we're going to do in STARTREC. So just, by swapping from the conventional rectangular shaped legs, if you make this hourglass shape here, just by reducing the surface here in the middle, you increase the thermal gradient so much that the power factor increases by 80%. That's simulated. We want to demonstrate it. So the project works by developing those technological building blocks, as I explained before, based on the requirements of our end users, which are here. So end user steel maker. The second one is a pellet boiler manufacturer, and the third one is an RTG producer, giving us their requirements, and then according to what we can develop in the technological building blocks, we will choose the best combination of module, of material sintering, of assembling, of integration to provide the best performance for those demonstrators. So that's the first use case. So you see here in the steel mill, a rolling mill, the steel slab, which has a temperature of about 1100 degrees. And the thermoelectric generator is suspended above it. So it's a small one, it's from a private trial. So the heat is going to the hot face of the tank. And of course you have to remove the heat on the other side, on the cold side, so that's water circulating and removing the heat, and this hot water can be used elsewhere in the mill, combined heat and power. Second use case is the pellet boiler, which Maarten has already showed, and the RGS is the third one. So I'm thanking you for your attention. I have helped setting up the project. Now the project will be taken over by my colleague Guillaume Savelli, who is the coordinator and technical manager of this project and the TE expert on this. So please address him for all questions. But for the moment, I can try to answer your questions. Thank you.
And then, yes, so we opened the possibility to ask questions, of course, and then as we also have the other speakers, yeah. We can also have other questions for them. But now maybe for Jean-Yves, if there are any questions. Yes, this one here. Yeah.
So I don't know if I missed it, but what are the implications of the segregation on the chemical segregation due to solidification structures on the thermoelectric properties?
Well, I'm not sure I can answer this question, but to me as a layman, I could expect that if the ideal material is designed as an alloy silicon germanium with evenly dispersed doping agent, that's the best situation, and whatever deviation from this ideal situation would be detrimental. So you see, we have a 4ZT. We assign it to the cracks because the electricity is not going through, but which share is owned by the cracks and which share by the segregation, I don't know. So we need to work on both issues actually.
Because for me, the additive manufacturing techniques limitation with thermoelectric application has always been this dendritic kind of.
Yes.
And I wonder if there's any way of.
So one major issue is the thermal gradients around the laser beam. So we want to mitigate this by heated plates. So we have already demonstrated this with other materials. With a heated plate, building plate at 500 degrees, you solve a lot of problems of mechanical tension already. And second comes the annealing.
then maybe I can comment. Sorry,
Yeah,
No,
Bruno.
you can.
why not thinking of staying in the additive manufacturing realm, using binder jetting techniques so that we use powders, which is common to our solution, and then use sinter, and then maybe you use orthostatic pressing, as you were mentioning.
Yeah, well, that's a very good idea, and that's in the plans. But we have only two people in the team, and well, plus supporting staff. But yeah, it's in the plans. But that's of course a good idea. Yeah.
Okay, thank you, Jean-Yves, for the presentation. I have one question related with the nanostructure.
Yep.
It will be maintained, the type of nanostructure, during the operation of the device,
Yes, definitely.
even being operating in such a high temperature.
Well, I'm not sure I can answer this question. The fact is that thermoelectric generators based on this material, silicon germanium, have been proven already. I mean, Maarten could mention that. We have made in previous projects demonstrations, so not years of demonstrations, but hours, and they remain in operation, and there are RTGs working with silicon germanium, and they work. I mean, I'm not expecting major changes, but of course that's equivalent to some annealing, yes.
Any more questions directly to Jean-Yves? I'm also asking the people remotely. If not, maybe the three speakers have cross questions between themselves, among themselves. Is there maybe how?
Maybe I can add one thing. You probably guessed that RGS is a key partner in STARTREC. So we have long cooperation on this material, silicon germanium, and that's why I always several times mentioned to Maarten for some help. A lot of these ideas which I exposed here will be worked out by RGS.
There's room for cooperation between the projects. Yes, Hao?
Yes,
You wanted to...
I want to bring this topic up. Is the first the cost of germanium, and the second is at this temperature above 600 degrees, and the availability of heat. What's your idea? What's your comments on that?
Well, I mean, Maarten will also answer, but our experience in previous projects with high temperature tags is really bringing the heat to the material. Because the source may be of high temperature, but you have all these layers in between, anti-oxidation, thermal protection, and whatever. And it is definitely an issue. Thermal transfers are an issue, and that's also why we have this building block on thermal transfer. We are using a lot of simulation in the project to see how important it is, but definitely you're right. Bringing the material to the right temperature is definitely key to the success of the tank, yes.
Yeah, let me add one comment.
Maybe you want to come closer to the microphone.
The microphones are
Okay.
So I put quite some emphasis on system integration in my part of the talk, and I think that is what this new program is about. Because what we have seen in the past with any cases of waste heat, if the system has been never designed for such a recovery, they are not directly suitable for this kind of recovery. And then I'm talking about waste heat, but the same is valid for any combustion chamber. The function of a combustion chamber was to get heat out at 70 degrees Celsius to heat up a building, for example. And so the internals of such a furnace has never been suitable for cogeneration at all. So the next step here is system integration to make sure that you make a design with an overall perspective, basically of a new system. And, for sure, it might be a challenge, but the higher you get with temperatures, the better this works.
Yes, I mean, you're absolutely right. We need a system integration. But when it comes to system, I mean, it's a real case that really hurted me, because that was several years ago that we also tried to promote this to heavy industry as a metal, not steel, but aluminum. They also have this solution when we say thermoelectrics is a solid state solution. It can convert heat into electricity. They are very excited. They knew nothing about thermoelectrics. Then they say, okay, come and introduce your technology. Then we say, yeah, this does this, and he asks, how does the system looks? Then we say we need the cooling water at the cold side to create delta T. And then this guy looked at me as I'm the biggest liar in the world, because he thought that, because he told me that I told him that this is solid state solution. And then in his head, if we need cooling water, the system is not solid state anymore. It's a completely different thing we're talking about, because you can imagine, right? In steel industry, if you need to run the cooling water, itself is a system. It's a closed system. How do you get the water loop and without leaking, and also let it work, not to say 10 years, but even 2 months, it starts to degrade. So you're absolutely right. It's really a system project here. We need to take everything into consideration.
Any more questions, comments? No, I don't see questions from the remotely connected people. Well, I think if there's no further question, then I think we can close here. I think we have to remind again what Hao presented in his last comment, industrial workshop that we want to organize at the end of September. And yeah, I would recommend everyone to stay tuned on our social media and website to get informed about this event, and people are invited to take part, especially if they have ideas and requests on the materials and systems for thermoelectrical solutions in their companies or processes. I thank again the speakers. Thanks to Maarten, thanks to Hao, and I think we can close it here. Thanks for being in our webinar, and stay tuned. We will have another webinar soon, maybe after the summer. Bye everyone, thank you.